So, for this top one here, where does my chlorine go? Does it go on carbon A or carbon B? The chlorine goes on carbon A. Right, the hydrogen goes on the least substituted carbon. The halogen goes on the most substituted carbon. So we're going to put the halogen on B. Where does my bromine go? B. Again, it goes on the most substituted carbon because that's going to make the most stable carbocation. Now, I stuck my bromine between the two methyl groups. It doesn't matter as long as that bromine is on that carbon. However you want to draw it, it's fine, right? They're all going to be the same name. They're all going to be 2-bromo, 2-methyl butane, regardless of how I have the bromine coming off that carbon, as long as it's on that carbon. So don't stress over that, right? Just make sure that it's on the right carbon. All right, so we can add HX across a double bond, hydrogen on one side, halogen on the other. We can do the same thing with water. Okay, so this is hydration of alkenes. It's a hydration. You're going to add water across a double bond. You're going to add H to one carbon and OH to the other. And your product is an alcohol. Now, you have your double bond of water. So if you just take an alkene and you mix it with water, nothing happens. It's like boys and girls at a junior high dance. Water's on one side, double bonds on the other. They don't mix. All right. You need to add a catalyst. This analogy falls off really fast, right? But you have to add a catalyst. So the catalyst here is sulfuric acid. The Boone's Farms of no cheap wine references. Okay. Um, and that will cause you to make an alcohol. So this is our catalyst. If we don't add sulfuric acid, nothing happens. So a catalyst speeds up the rate of a reaction by lowering the activation energy of the rate determining step, but it itself is not consumed. You could technically get the sulfuric acid back out of this reaction at the end. So the sulfuric acid isn't really changed. And when something's a catalyst, it means you need a small amount of it. In theory, we could do this, and we could have an entire mole of 2-butene, which is 6.02 times 10 to the 23rd molecules. We could react all of those with just one molecule of sulfuric acid, because the sulfuric acid keeps getting regenerated, or the acid keeps getting regenerated step after step after step. So each time you make a product, you regenerate your acid to go react with the next product. So you only need a small amount of catalyst to do your reaction. So it's not like you need a 1-to-1 ratio of alkene to sulfuric acid. You need a 10-to-1 ratio or a 100-to-1 ratio. So you just need a little bit. So let's look at the mechanism of this reaction. Right, we're going to go with this guy, same one we just drew. So something we need to get in the habit of doing is whenever you see water or an alcohol with sulfuric acid, the first thing that's going to happen is that acid is going to react with that water or that alcohol. So you're going to have H2O, and you're going to have sulfuric acid, and the lone pairs on your OH are going to attack one of the hydrogens of sulfuric acid, and then again we're going to push electrons onto this oxygen. So we're going to put a proton on our water, and we're going to make a sulfate anion. Now, this is just H3O plus. Okay, that's the H2O with the extra proton, H3O plus. The H3O plus is what actually reacts with the alkene. The sulfuric acid doesn't hang around long enough to interact with the alkene at all. It goes into the solution and immediately protonates water. And then that protonated water, the H3O plus, is what actually does the reaction now. So now we can take our alkene. I'm going to draw out the H3O plus. Now here, the electrons from the double bond attack a hydrogen and push electrons onto the oxygen. So you might be thinking, well, the oxygen is positively charged. Why don't I add to that? The reason the oxygen is positively charged right now is because that oxygen is making too many bonds, right? It's sharing too many electrons. It doesn't want to make any more bonds. It just wants the 2 electrons that it gave that hydrogen back, right? And the way it gets those electrons back is something goes and grabs that hydrogen off of it, and it pushes the electrons back. This is directly analogous to when the double bond attacks the hydrogen of like HBr, and we push electrons onto the bromine. This is the same thing. We're attacking that hydrogen, we're pushing electrons onto the oxygen. Kind of doing the exact same thing. That's going to lead to our carbocation. And we're going to have water. Now at this point, the lone pair on our oxygen of our water is going to act as our nucleophile. Those electrons are going to go add to the carbocation and going to make a new carbon-oxygen bond. So I use those electrons to make a new bond. So those lone pair electrons are now the electrons that are in that bond right there. I'm one hydrogen away from the product, right? The product's an alcohol, I have one extra hydrogen. So another water molecule will come in, grab that hydrogen, will make the product, I'll move over here, will make the alcohol product, plus regenerates H3O plus. So each time I make the alcohol product that I want, I regenerate H3O plus, so that H3O plus can go react with the next alkene and start the whole process over again. So every time you do this, every time you make a product, you remake H3O plus. Eventually, when you run out of product or run out of alkene to react with, you'll just have H3O plus, and if you could remove all the water from the reaction, you get your sulfuric acid back. Practically, it's just H3O plus and sulfate, but you get rid of all the water, your sulfuric acid will come back. So that's how that works. Now, you can see a lot of parallels between this mechanism and when you add HBr, right? Your alkene adds to a hydrogen, but your hydrogen gives up its electrons to what it's attached to, right? That's this step. Right? Then whatever your hydrogen had been bonded to, then attacks the carbocation, right? When it's HBr, it's Br minus it attacks. When it's H3O plus, it's the water that attacks. So there's a lot of parallels. So there just has one extra step where I have to get rid of the extra hydrogen. Because of that, because the mechanisms are so similar, Markovnikov's rule applies and explains all your selectivity of how these reactions work. So Markovnikov's rule says the hydrogen goes to the carbon with the most hydrogens, and that the other thing attached to that hydrogen goes to the carbon with the least hydrogens. So we can just use Markovnikov's rule, and we know that we're going to put the OH on carbon A because it has less hydrogens on it than carbon B. You might also see sometimes, oh, let me sure you can actually read that. You might just see cat H2SO4. That's just short for catalytic, so a catalytic amount of H2SO4. So I'll write it either way. Like the lazier way is where I don't write the catalytic part, where I just have water, sulfuric acid. But if you see water and catalytic sulfuric acid, it's going to do the same thing. So here, again, we're going to put the OH on the carbon that has the least hydrogens. So someone in the early class asked me, like, why does this work? Why can we just predict this? Remember, it goes back to carbocation stability, right? If we have this structure, right, and we add, so we have this, right, and when we add, we have two possibilities, right? We can make two different carbocations. You can make this, where you put the hydrogen on the more substituted carbon, or you can make this, where you put the hydrogen on the least substituted carbon. What type of carbocation is that? How many carbons is that positively charged carbon directly bonded to? It is a secondary carbocation. It's bonded to two different things. That's secondary. What kind of carbocation is that one? It's tertiary. All right. That's a tertiary carbocation. Which one's more stable? Tertiary. Right? So remember, your molecules are always going to kind of take the path of least resistance. Since this one's most stable, it's made more, or made the most, or made exclusively. We make the one that's more stable. So that carbocation is then where the water can act. Right? So Markovnikov's rule kind of rolls all this up into one little kind of like neat thing where it's like, hey, put your hydrogen on the carbon that has the most hydrogens, put your other thing on the carbon that has the least hydrogens, and the way that works out is that always has you make the most stable carbocation. So instead of having to, for every single solitary structure, for every reaction, draw out both carbocations and go like, oh, this one's more stable, so that's where I'm going to put my hydrogen, so then that's where my oxygen is going to go, or my halide. We just roll that all into Markovnikov's rule and can just shortcut it to hydrogen with the most hydrogens, other thing with the least hydrogens, and be good. So we can do this with water. This can also be done. Hydration is, I guess, kind of an air quotes here. Hydration with alcohol or alcohols. Right? So you can take an alcohol, and I'm just using R to kind of stand in for any generic alcohol, and you can treat it with sulfuric acid. And instead of making alcohol products, you're going to make ethers. Right? So basically replacing one of the hydrogens on water with a carbon. So we can do right all the same rules. The mechanism for hydration with water or hydration with alcohol is exactly the same, right? So you're going to put your hydrogen on the least substituted carbon, your oxygen on the most substituted. So that's going to be your product, right? Hydrogen goes over here, oxygen goes on the most substituted. Seems reasonable? Now, I don't want to go through and redraw the mechanism. What I will tell you, the mechanism for doing a hydration with an alcohol is exactly the same as doing a hydration with water, except for you erase one of the hydrogens on your water and make it a carbon. But then everything else is exactly the same. That makes sense? Right? So instead of having 3 hydrogens on your H3O plus, you'd have 2 hydrogens and a carbon. but then everything works exactly the same. So you're just carrying that carbon through instead of carrying that one hydrogen through the whole mechanism. But it's the exact same thing. So far, so good? Feel like you got a pretty good grasp on this? These two things seem doable? All right. So I told the earlier class, let's make this less doable now. Okay. So one thing you're going to notice is I try to group everything that we do by mechanism. So these two things have the same mechanism, and then there's going to be a bunch more reactions that are all going to share a mechanism. But there is a kind of a consequence of this mechanism where we have a carbocation, and that is that carbocations can rearrange. So once you have a carbocation, your molecules are able to move hydrogens or other carbon groups to make more stable carbocations. So what this means is, from now on, every time you generate a carbocation, you need to look at it and think for a second, can I move something to make this carbocation more stable? When that happens, it changes the product you expect. So you guys are all very smart. First test be damned. All very smart. Right? And you look at this and you're like, I got this. I know that I'm going to put the hydrogen on A and the bromine on B. No big deal. Wakefield's going to throw a C in there. And he's going to say, no. The product actually, bromine goes on the yet to be discovered third option of C. Right? And the reason this can happen is carbocation rearrangements. Right? So I'm going to show you how this happens, and not just be like, figure it out, surprise. Right? So, right? First of all, let's figure out what groups can move. In a straight chain, only H's and methyls can shift, can rearrange, can move from one carbon to another. So moving them, these movements are called 1-2 shifts. So let's look at the thing that we just did. Right. So we think about the mechanism. We're going to add to our double bond. We're going to make a carbocation. What kind of carbocation is that? It is secondary. This is a secondary carbocation. We're going to pretend I wrote carbocation there. All right, so whenever you generate a secondary carbocation, you need to look at the carbons on either side and ask yourself, what happens if I were to move a hydrogen, or what happens if I were to move a methyl group? right? Your goal when you do one of these shifts is as soon as you do the shift, you get a more stable carbocation, right? So if I look at this orange carbon, if I were to move a hydrogen from that orange carbon, I'd make a primary carbocation. That is worse than a secondary carbocation. So I'm not going to move anything from that carbon. But what if I look at that carbon? This will make it blue, right? What if I move a hydrogen from there? What if I take this hydrogen and shift it over? So what happens is this is called a 1,2 hydride shift. That's a D. There you go. So hydride is the term we use for a hydrogen that has a negative charge. So this hydrogen right here is taking its 2 electrons and it's hopping over 1 carbon. So you can think of it as we're going 1, 2. So that's where the 1, 2 and the 1, 2 hydride shift. You go from 1 carbon to the adjacent carbon, from carbon 1 to carbon 2. Right, when this happens, that hydrogen took its electrons with it, right? Picked up and took its electrons and used its electrons to fill the empty orbital that is the carbocation, but it left a carbon short electrons, right? Because it took its 2 electrons that it was sharing with its carbon and moved. So now I have a tertiary carbocation that is more stable than a secondary carbocation. So I'm going to do that shift. Now, this is the carbocation that is around for my bromine, for my bromide to react with. And that's going to give me the observed product. So you need to look at every secondary carbocation that you make and think, can I shift something from 1 carbon over to get that from being a secondary carbocation to being a tertiary carbocation? So the things you're looking for to kind of clue you in that, hey, I might be able to do a carbocation rearrangement, right, is your double bond. Your double bond is beside a tertiary carbon, right? So if I move a hydrogen, if I pulled a hydrogen off of that carbon, I'd make a tertiary carbocation. So if your double bond is beside a tertiary carbon, that means that when you generate the carbocation, right, this is what we just did, right, that secondary carbocation is beside a tertiary carbon, it can take a hydrogen from it. Or your double bond is beside a quaternary carbon with methyls. We're only allowed to shift methyl groups. So if you have a quaternary carbon and it has a methyl group, you're able to do a 1,2 methyl shift. So again, you're going to make that carbocation. Right? It's going to be secondary. You're going to take one of your methyl groups and you're going to move it over. So that carbon is going to take its 2 electrons with it. So this is a 1,2 methyl shift. And now I end up with a tertiary carbocation. Then I can add my nucleophile to that positive charge. So you're looking for your double bond to be beside a tertiary carbon or a quaternary carbon that has at least one methyl group on it. Right? So as long as there is a methyl group on that quaternary carbon, you're good to go. So you're going to look at this and you're going to say, okay, I know the water and sulfuric acid does a hydration, and I know that's going to make a carbocation. Right? So you have to think, okay, can this rearrange? So you're going to make this carbocation. Everyone on board with that? Right? Hydrogen's over here. Now, I'm going to take one of my two hydrogens and I can shift them over, and they're going to take their two electrons and fill that carbocation. Right, so this is secondary. This is now tertiary. This is now tertiary, so that's more stable, and I move the methyl group over. Now I'm going to add my water to that more stable carbocation. So the alcohol I'm going to get is that. Same thing here. I have one methyl group, so I can do a shift. I'm going to make that alcohol. If I have no methyl groups, I can't do a shift, right? So if I have a quaternary carbon that has no methyl groups, you don't have to worry about rearrangements. So if that last methyl group was an ethyl, then there's no possibility of a shift. There's no hydrogen to move, right? Because it's quaternary, and there's no methyl group there. So I'm just going to do that. I don't have to worry about a rearrangement. Here, my tertiary carbon isn't right beside my double bond, so I'm not going to do a rearrangement. Doing a rearrangement is a lot of work for a molecule, so it needs to get paid off immediately. When you do that 1-2 shift, you need to end up with a more stable carbocation or a more stable molecule immediately, right? You can't do something like, well, I have this carbocation, so if I move this hydrogen, I'll get another secondary carbocation. But then if I move this hydrogen, I get another secondary carbocation. But then I can finally move the third hydrogen and get a tertiary carbocation. It doesn't work like that. Molecules fail the marshmallow test, right? They want immediate gratification. They want to be immediately more stable. They don't like long-term plan and go like, well, if I move this hydrogen and then I move this one and then finally I'll get more stable. They're like, no, if I don't get it right now, I don't want it, right? So you can't like walk your carbocation down a chain to get to the more stable position. If it doesn't get there immediately, it doesn't happen. So if you're beside like a 6-membered ring, right, this hydrogen is able to move. So I'm just going to end up with that chlorine on the ring, right? So I'm going to get this, then this hydrogen will move over, do a 1-2 shift. It will make the tertiary carbocation, and then my chloride can add to that. Fair? Going back to the idea of having to get paid off, having to become more stable whenever you make your move. If you make a tertiary carbocation, you're already as stable as you're going to get as a carbocation, right? So it doesn't do any good to move a hydrogen and make a different tertiary carbocation because you're already as stable as you can be. So there's not going to be any rearrangement. So there's no rearrangement. So there's no rearrangement of tertiary carbocations in straight chains. So if you make a tertiary carbocation, you're golden. Nothing's going to happen to it. You're just going to make the product you would have expected like 20 minutes ago in a simpler time. Feel good? Feel semi-confident? No one's crying here. The one person with their camera on is not crying. We're good. This is all right. Thank you for not crying, Zoom guy. All right. So I made the specific caveat that in a straight chain, there's another type of rearrangement that is everyone's favorite, and that is ring expansions. Right? And as the term ring expansion implies, so ring expansions, you go from a small ring to a larger ring. Oftentimes, you'll go from a secondary carbocation to another secondary carbocation, but your payoff, where you're becoming more stable, is you go from a small ring that has a lot of angle strain to a larger ring that has less angle strain. So if you remember, like a 4-membered ring, right, has bond angles that are basically 90 degrees. That's really far from 109.5. So there's a lot of inherent strain in that 4-membered ring. But when I go to a 5-membered ring, I release that strain because I get closer to being 109.5, right? So even if the carbocation stays the same, the molecule overall is more stable because my ring is less strained. So as a general rule, right, rings expand from a 3-membered ring to a 4-membered ring, a 4 to a 5, a 5 to a 6. We don't get any bigger than 6. Right, because we've said that 6-membered rings have effectively no strain, so I can't improve on that. If I have a 6-membered ring, I'm not going to get any bigger or any smaller. All right, so what you're looking for when you're doing a ring expansion is you want to have, put the group here, you want to have a double bond beside the other one you interact with is 1 carbon over from the ring, is adjacent to the ring. And the carbocation that you generate needs to be, again, adjacent to the ring. So this is on this carbon here. Right now, let us count. 1, 2, 3, 4. And I like to make the ring that has the carbon that has a positive charge 5. So if I have a 4-membered ring, the carbon with the positive charge is 5. If I have a 6-membered ring, if I have a 5-membered ring, that carbon becomes carbon 6, right? So what you're doing here is you're going to break the bond between carbon 1 and carbon 4 and make a bond between carbon 4 and carbon 5. So the electrons that are in between this bond right here, these electrons are going to shift out and add to that carbocation. So what that does is, and here's why I number, it's handy. On carbon 1 in my starting material, I had an ethyl group, right? I had this ethyl group right here. Nothing happened to that ethyl group, right? So it still needs to be on carbon 1. What was on carbon 5? Carbon 5 had a methyl group on it, right? I still need to have that methyl group. Now, electrons left carbon 1, right? Carbon 1 was sharing electrons with carbon 4. Carbon 4 said, screw you, man, I'm going home. And took his electrons and moved, right? And left carbon 1 short electrons. So carbon 1 gets a positive charge, right? Because electrons left that carbon, so it gets a positive charge. So in this case, doing the ring expansion gets me a more stable ring, right? I go from a 4-membered ring to a 5-membered ring. Something that has bond angles of like 90 degrees to something that has bond angles of like 108, which is way better. And I go from having a secondary carbocation to having a tertiary carbocation, right? So I get paid twice. I get paid by making a more stable carbocation, and I get paid by making a more stable ring. Now I can add my bromine. And that's my product. People in Zoom already leaving. They're like, I'm out. I'm not doing this crap anymore. I'm done. My body can't take this anymore. Right, so I like to number all the carbons so that it's just easier to see where everything goes from one thing to the other. I might just call it here because you are slightly ahead of the other class. We spent 4 minutes trying to figure out if a video was on the YouTube playlist. So, beginning of class. So we'll call it here. We'll end on this slide. So everyone, take it easy. Person who left early, I guess it was fine.